this one. This is a brand new one, so I'm not actually sure how long it'll take. So I'm hoping it'll probably be around 35, 40 minutes, but I don't know. But without further ado, we'll get going. So what I'm going to look at is four main things. What is design overlift? Why use design overlift? I'm going to look at the types of design overlift or settlement compensation and the benefits of using design overlift and settlement compensation. Now, what is design overlift or settlement compensation? Well, I'm hoping that most people have got an idea because there's the clues in the title. It's where we overlift the track above the design level to compensate for settlement, basically. So after settlement, we want the track to be somewhere where we originally designed it. Because what happens conventionally is we will lift track to a design and it will settle underneath under traffic, under dynamic loading of trains. Now there's various graphs explaining settlement. I think people misunderstand the extent of settlement and actually how much it affects the track. And there's some really interesting graphs done on various research over the years. If you have a look at this one, and it's a bit of a trend in all the graphs I'm going to show you. The lift you're going to apply is at the bottom, and the settlement's up on the left. And as you can see, if you're putting a 5 mil lift on, you could expect something around 7 or 8 mil settlement. If you're putting 10 mil lift on, probably something around 12 or 13. So until you really, and what the graph's saying is here, you can see where it starts to level off, probably around 17 mil. So only when we really apply lifts of 17 mil and above does the lift start to outweigh the settlement. Now, there are various reasons for this. Small lifts, 5 or 10 mil, don't really give the ballast enough room to reconfigure itself. So all we're doing is creating spaces in the ballast, which ultimately will get filled again. And also when we lift track, particularly with tamping, the ballast isn't quite consolidated again, so we'll have points of ballast on edges of others, and under the dynamic settlement of trains, these will break, causing ballast damage, and hence it will settle a bit further down than what we lifted it. So when we limit lifts to 10 mil, close tolerance lifts and stuff like that, it's sometimes I've got my head in my hands sometimes thinking, no, what's the point of sending out a machine? So we'll have a look at another graph. Tells a similar story again. Lifts on the bottom, settlement. Again, this one's saying you apply a lift of 10 mil. Again, very similar story, 12 mil of settlement. Apply a lift of around 17, and then you get about 17 mil of settlement. So again, this one's a very similar story. Only when you get above 17 mil do we start actually, are we in the black basically with lifts? Are we in the positive? And I'll go on to another graph. This is an Austrian graph, and this is again saying very similar. You're probably getting to see the shape of the settlement curve. Again, this one's probably a little bit lower, around 15 mil, where settlement where lift outweighs settlement. And the theory on this one is they talk about remain lifting. Now, remain lifting is a lift you want to remain on the track. So I'm assuming if you put a 20 mil lift on, most people want a 20 mil lift to remain on the track. So in that instance, I just show you. So if you're putting a 20 mil lift on the track and use that formula, you'd be looking at something like a 35 mil lift to compensate for settlement. So those graphs are saying the minimum lift should be 15 or 17 mil. Because only then are you really going to get outweighed by settlement. Is it going to be even? And if you want to compensate for settlement, you need to apply bigger lifts, hence design overlift. Now here's another graph. This one's a bit more. This one's a bit applies. This one's a bit less actually. This is an interesting graph because this is again, if you might notice anything below 10 mil isn't even on the graph because it's just it's basically saying it's not worth lifting below 10 mil. Now, it's a pretty simple formula. It's 4.2 times the logarithm of the lift, and then you subtract 4 from that. So this is saying, theoretically, if you had a 20 mil lift, the track is going to settle 8.6 mil, so you need a 28.6 mil lift. Now, on the trial, I actually did a trial on this on settlement, and I'll come back to the trial later on for a completely different reason towards the end of the presentation. But on the trial, when I applied a 20 mil lift, we had a settlement of 13.7. Therefore, the nominal lift, sorry, should have been 33.7 mil. Now, if I just go back up to those graphs, that is very close to that 35 mil on that equation from the Austrian stroke German graph. So as you can see, this one probably under-egged settlement a bit, but the message I'm trying to get over to everyone is I don't think people realise how much the track settles when we tamp, and particularly when we stone blow because of the residualist we apply. This presentation's mainly about tamping because it's design overlift on tampers, but I did have to mention stone blowing because a well-known fleet engineer and a colleague of mine will be listening. I don't want to incur his wrath. So, but the point I'm getting across is settlement is underestimated on both tamping and particularly stone blowing. So now it is a trial that Placid did as well, which I thought was really interesting. So at the very bottom, we've got the before tamping, so that's your track as it is. Then we've got our target in red. So as you can see, we're looking at about probably 37 mil lifts in its biggest lifts of 37 mil. Now, immediately after tamping, you can see we're probably between 18 mil low in places, 2 mil low in others, and a month after we're even lower. We're between 23 and 10 mil, so we're between 10 and 23 mil lower. So we're well lower than where we want to be because of settlement. Now, Placid did a trial using 50% overlift. Now, I'm going to come on to the types of overlift in a minute, but 50% overlift is basically 50% of your applied lift. So if you have a look at this graph, because of the 50% overlift, we're theoretically well above our target, but you get that immediate settlement under the machine, under the bogies and actual weights of the machine. So straight after tamping, you can see we're between -4 and probably 8 mil above. So you're pretty close to where you want to be. And a month after tamping, you're there or thereabouts. You're only between 4 and 8 mil below. So you obviously you can see there it's a much better result, much closer to our target. So again, that is the reason why we use design overlift or settlement compensation. We are essentially compensating for settlement. So let's move on to types of overlift and settlement compensation. You can do a manual design where you can use one of those formulas. You can do a design and you can use that remaining lift formula to increase your lifts to apply for settlement, or you can have a little bit on the side of caution with that last graph I showed you, which under-egged settlement a bit, underestimated settlement a bit, which would mean you wouldn't apply as much overlift on your design lift. So if you were a bit or lacking confidence, or were just wasn't quite sure, you could err on the side of that settle if you wanted to do manual design. But I'd definitely recommend using one of the mechanized overlift methods, which I'm going to explain now. Now there's WinALC, where you've got percentage of applied lift and overlift for England. You've got Smart ALC, where again you've got percentage of applied lift and something called Differential Overlift. And you've got CMS machine DTS Overlift, computer measuring system. That's just the software on the tampers. So our high output fleet have this on our 093X and 2X machines. Or we've got our pick machine settlement compensation. This is Placer Intelligent Control, and this is on our latest, newest machines, our 09 4x4 4S dynamic machines. And you have also got something called Crosslevel settlement compensation, which is applied to the high rail, which is a really useful feature on the machines as well, and a form of overlift, which I'll explain. So the first one, WinALC, and as I mentioned, the first method's pretty straightforward. It's a percentage of the applied lift or the design lift you want to apply. You can also use it on a measuring one. You could do a WinALC measuring one, or you could use it on a geometry where you've done a design, and then you would put an overlifting value in there, and you may want to put a minimum overlift of 5 mil and a max overlift of 15. So on WinALC, the max overlift you can put on is 50%, which I've put in there, which sounds a lot, but generally, if you were doing a WinALC run, your lift would be around 25 mil, your max lift. So 50% of that would be what? 12.5 mil. So 12.5 mil on your 25. And you can have, you would be, 37.5 mil, not a massive lift, to account for settlement, quite similar to some of the equations we've doing. And you can put a min and max overlifting value, as you can see in there, or you can use the manual graph. So what you do, you click the little box there, and you would use something called design overlift. Now, this goes back to a graph, and I think Stephen alluded to this at the during the introduction. Dave Marriott and part of Derby Research, maybe people like Don Asprey and a few other people did some research, and they come up with this graph. Now, this was, as Stephen said, this was quite a while back during the 80s. And as you can see, I think this was a really good graph, but unfortunately, it may have given Design Overlift a little bit of not a bad name, but it may have put people on edge or a bit of caution, because if you apply a 25 mil lift, so your required lift on your y-axis is 25. If you would look at the graph, it's probably going to apply a 48 mil lift. So you're airing on, you're looking at quite big lifts. So obviously, if you've got the stuff like overhead line equipment or tight clearances, you need to be very careful. And also, the other thing you need to take into account when you're applying lifts like this is your ballast conditions, because once you get into the realms of 48 mil, you're going to be using significant amounts of ballast on your site for lifting. So there's the two WinALC methods. So when you go into, I've just put an example on here. So if you're in work mode, this was actually a geometry file. So this was a design. I put in overlift there. I think this was on 50%. So as you can see, the level corrections, 15 mil, overlift value 7 mil. So you can actually see what you're overlifting. You could actually run this before you could actually simulate this in work mode before you get on the machine, so you can actually have an idea of all your overlifts before you go out and apply them if you're concerned. So you can go on all your stations, go through the simulation, and you can take a note of all your overlifts, so you know exactly what's going on. Now, moving on, Smart ALC. So again, our 094x44S machines have Smart ALC. And you've got two options on this one again. The first one, again, very similar. It's the percentage of applied lift. As you can see, you've got a minimum and a maximum. The only difference here is, and be wary, it's not limited to 50%. In fact, it's not limited at all. So just be very, just be a bit careful. It's not a method I really like using, the percentage of the lift. I would much prefer this second method and a couple of other methods, which I'm going to explain in a bit. And differential overlift is something relatively new because we haven't had these machines very long, but I think it's a much better way of applying overlift. So what you would do, you would click the box for differential overlift, and you would put your percentage in of how much differential overlift you wanted to apply. Now, you would almost certainly always apply 100% using differential overlift, and I'll explain why now. Firstly, I just wanted to show you a simulation again. This is the same screen in work mode on Smart ALC, and as you can see in the top right-hand corner, you can see your total lift and your overlifting value as well. So differential overlift, it's basically designed by the Austrian Federal Railway, and it calculates the mean rolling lifts over 30-metre sections. Put an asterisk there because 30 metres is the default setting. You can change that to whatever distance you want. And what that means is it's the mean lifts against your applied lifts over 30 meters. So 15 meters either side of your applied lift will be the average. And if the rolling average is below your design lift, it will apply the difference as overlift. So if you put 100%, so it's a percentage of the entered of the difference applied. So if you put 100% in, it just puts 100% of the difference. So if the difference between applied lift and the rolling lift is 10 mil, it will apply 100% of the difference, which is 10 mil. If you were to put 50% in, for instance, it would only apply 5 mil. So that is why I would always say put 100% in, because we're not talking about large values here. Now, if the rolling average is above the design lift, then it doesn't apply overlift, which to me is a really good feature. So what it's saying, and I've got a graph which makes it a lot easier to understand. So what it's saying is, if the rolling average is above your lift, it won't apply overlift. So it's not going to apply overlift to high spots, which to me is the disadvantage of percentage, because even if you've got a high area, you might not want to apply it because you've got a very low lift on and you don't want to overlift it. So say if you've got a high area with only a 5 mil lift on, you're still applying, and you've got 50% in your overlift, you're still applying another half of that lift onto the high area, which you don't want to do. So the beauty of this is it doesn't apply overlift to high areas, and it's taken into account of the mean lifts, not just where you are, but 50 meters either side. So it's a very smooth way of applying overlift. I think this is a really good method. It shows the overlift value and total lift in your work mode, and you can simulate the overlift value of the entire site before you tamp, which is really good. So I've put these screens up because a lot of people miss it. It's very hard to get into the menu, because you have to go into additional work mode settings. There's basic and advanced settings, so you have to click on additional work mode settings, and then if you go into differential overlifting, as you can see at the bottom, the average is 30. You can change that to 20 maybe, and if you click the graphic representation of overlift, it also puts a graphic representation of the overlift in work mode, which I'll show you, which I'll show you shortly. And then you also have to go in your advanced settings in work mode, so it's a bit fiddly to find. And then you put your overlifting value in there. You can see I've put 100% and I've clicked on differential overlift. If I don't click on differential overlift and put 100% in, it will double my lift. So if I've got a 30 mil lift, it will apply 60. So be very careful. Just make sure that when you're using differential overlift, not only to apply the 100%, but to click the box. So this is trying to explain it more in a graph. So the top graph is your design lifts or your applied lifts. Like I said before, it could be from a geometry file. It could be, you could do a measurement run, and you could export it into Excel and plot it on a graph. Either way, these are your design or target lifts. Now, the graph below is the rolling averages. Now, just for the example, I changed this to 20 meters. So this is a 20 meter rolling average. So instead of 50 meters either side of applied lift, I am now looking at 10 meters either side of the applied lift. So as you can see, the orange line is the rolling average there. So you've got applied lift and you've got the rolling average underneath. Now it shows you all three lifts in one go. So again, you've got your design lifts in blue. You've got the rolling average at 20 meters, like I've explained. And as you can see, the green line at the bottom is actually overlift applied. Now that's at 100%. So if you can see, the overlift applied essentially is the difference between the design and the rolling lift, where the design lift is higher. And it's 100% of the difference. So it's the difference between those two lifts is what is applied as overlift. And as I mentioned before, where the rolling lifts are higher than the actual lift, as you can see from the green line, it doesn't apply any lift at all. So again, this is why I think it's a really, really good method. And I put a note on the bottom because the tamper uses an asymmetric chord measuring system for this, if you go in the reverse direction or the opposite direction, it will come up with different values. And as you can see on there, this is differential overlift. So as you can see on so you're looking at the very bottom of the graph for those that aren't familiar with well, I'll just go through the graph. The lining is the top from left to right. So that is basically the curvature. The super elevation is the cant. Then you've got longitudinal level. Each one of those rectangles is a vertical curve. So you've got some hogs and sags in there, not hags. And then you've got your shifting value, which is your front offsets, which is what your slews are applied as. And then the very bottom graph is the one that we're interested in. It's got the lifting, so that is our level correction. So the blue line is our level correction, and the orange line underneath is the overlift applied. So, and if you go at the top, it shows you your total lifting and your overlifting value. Now, the sharp-eyed amongst you may have noticed that the overlifting value is negative on there, and people are probably thinking, well, if it's overlifting, why is it negative? So I'll show you why. It's not negative at all. What happens is, if we have a look at this, this is supposed to simulate a tamper's asymmetric chord measuring system. So you've got your front feeler trolley, which is far right, rear feeler trolley at the left. These are what tension the chords, because tampers use steel. Well, this type of tamper uses a steel cord as a measuring cord, and the middle dot is the measuring trolley. So what happens is, once we've overlifted the track, as you can see, the rear trolley is higher than its design position. Therefore, it's lifting up the measuring trolley above what it should be. So what the tamper does, so if we didn't have that negative value in there, we would be in a false position. Our design is saying that that measuring trolley should be on the green line, whereas in essence it's on the blue line. So what the tamper does, it lowers the front feeler trolley. This is virtually, obviously, hypothetically, whichever way you want to. So it theoretically lowers the level correction trolley to a lower point. So it then puts the working trolley on the green design position line, so it's in the correct place. So that is why you'll have sometimes see negative on the working mode, and that is merely the level correction on the front trolley compensating for the rear trolley being high. I hope I've explained that well, but that's the reason for that. So moving on, just excuse me 2 seconds. The next method I'm going to look at is DTS settlement compensation. And as the name mentions, it's settlement compensation when you're using DTS, because DTS, by the nature of it, is designed to settle a track, does it in a much more friendly way to ballast, does it on horizontal means as opposed to dynamic loading, much better way of settling the track, really good method, which I'm going to allude to in the results a bit later on. And as the name suggests, it's designed to compensate for the high settlement when using DTS. It's independent to other and different to other overlift options on the machine. So if we use, so work them independently. So if you're using DTS settlement compensation, then you shouldn't be using differential or win ALC or a percentage. You shouldn't be using two overlift systems on the same shift, but I'm pretty sure most people would know that. Should always be used when using DTS. And I'll put this for people who want to use it. The settings aren't on the DTS screens. The settings for DTS Overlift are on the measurement screen. So if anyone who is operating the machine or trying to find it, that is worth knowing. And what it is, this is on the CMS machine, as I mentioned earlier, computer measuring system machine. So we're talking about the high output fleet. And what it will do, your lift is on the bottom and the overlift it will apply is on the left. So it's not really a massively aggressive system, this at all. It if you put I'm just trying to read this, not that clear. If you put a 30 mil lift on, for instance, you're probably looking at a 13 mil of overlift, and it will put overlift onto a maximum of 22 mil. That system, quite a basic system. One of the first. I mean, those machines now are over coming up, some of them over 20 years old now, so it's not the newest system, but it's certainly better than using nothing when using DTS. This is the PIC system, Passive Intelligent Control, on the 09 systems. So as I alluded to before, if you go on the measuring screens, you can see settlement, compensation, and DTS. So it's not very clear to find. It's really hard to find DTS settlement comp. So then you would put whatever percentage you wanted in there. And what happens is, again, similar to the last graph or the next graph I'm going to show you, if you apply 100%, it's 100% of the graph. So if we have a look at this graph, for instance, this is a much more, there's a bit more theory in this graph. So I'm trying to look at 25 mil. I'm trying to look at 25 mil of lift there. So if you apply 25 mil of lift, it's going to put something like 10.5 mil, 11 mil overlift on if you put it 100%. So as you can see, not massive values. So again, I would range between 50, sometimes 25, 50, or 100%, depending on where you are, whether you're under wires, how much you think the track's going to settle. I'll go on to that in a minute. So there's your two overlift graphs. The PIC one, I think, is a far better graph. Take it, but then it's a lot newer graph, so it's had much better research done on it. And I'm going to move on now to something that's probably not that well known, but it's a feature. It's on the 08 machines as well as the 09. This one's called Crosslevel Settlement Compensation. Now, again, this is on the measuring screen, and it's the screen above. It doesn't actually say what it is, which is strange. You've got a settlement comp box there, and you've got DTS at the bottom. So if it's not DTS, then we have to assume it's Crosslevel, which I can tell you now it is, but it's not very well labeled. So what this is if you've got a machine there, you have your front trolley there, which is, and all these trolleys measure. This is they've got pendulums on, as well as tensioning cords for the measuring cord. The tension, they've also got pendulums on, which take into account the rail heights. So as you can see, if the front, and they just take measurements. So there's one at the front, there's one in the working area, and there's one at the rear feeler trolley. And if you've got a DTS machine, you will have one after DTS, which is part of the DRP measuring cord. So it's the rear trolley and the DRP measuring cord. If it's not a DTS machine, it'll just have the front, middle, and rear. And just to show you where they are on the measuring screen, you can also look at these digitally on here. So you can see what your cross levels are for your front, middle, and rear, and DTS if you're using DTS. Now, what it is, it's overlift for the rail with the most lift. So if you're on canted track, generally the high rail, not in all situations before I get trampled on, but in most situations, the high rail will be under canted, and it will require the most lift to correct. So for instance, if you're on a cant of 150 mil, you may be 20 mil out of cross level. So if you've got a 10 mil lift on your datum rail, it's going to apply the 10 mil or even 20 mil lift on your datum rail. It'll apply a 20 mil, and it'll then apply another 20 mil. So you could have a 40 mil lift on your high rail and only a 20 mil lift on your low rail. So for that reason, because you've got significantly now more lift on your higher rail, then it goes to reason that we will settle more. So this is designed to compensate for the initial settlement under the 20 to 25 ton axle loads of the on the machines, depending on which machine it is. It's an empirical curve, it's not linear. And so because it's an empirical curve, I can't really, there's no right linear straight graph to represent it, but there is an approximation of the formula is it divides the cross-level error by 2 and then applies the percentage of the cross-level error by 2. So for instance, I've made these figures easy just for the sake of the presentation. If you've got a cross-level error of 20 millimeters and you went to 25 mil settlement comp, then half of your cross-level error is 10 and 25% of that 10 is 2.5 mil. So the machine will add 2.5 mil onto your lift on the high rail, if that makes sense. If I was to put 50% in, it would then put 50% of that 10 mil and it would add 5 mil. So it's a very clever piece of kit and it's designed to compensate for the initial settlement under axle loads on high rails. So let's give a few examples. So this would be cross-level settlement comp, not using DTS. So as you can see, say if we started off with a low reading, with a low 15%, and you would watch the galvo, so you could go in the front of the cabin in the tower and watch the digital screen that I showed you. And you can see here we're out of cross-level by quite a bit on the front. The middle working area always corrects it to the correct cross level, and because you've had a few axles over it, the rear trolley is already reading it slightly out. So then you've got your 15% on. So what you'd do, you'd up that, you'd wait a machine length, and then you would up that cross level compensation by around 5%. You could estimate it. So the next time you come on, your front is out again. Your middle corrects it, and because you've upped the cross-level compensation and to a higher level, you check your rear, and it should also be 12 o'clock, which is the correct cross level. So moving on, if you were using DTS, this would be you've got to keep a bit more of an eye on it. So what would happen, as you can see, the right hand on the front, you'd be out of cross level. The working area comes on, always corrects it. You lose a tiny bit again because of the axle weight to the machine. And then after DTS, because DTS is settling the track, you may also lose more cross level. There are features on the DTS that take into account cross level as well, but by the nature of the beast, you may lose a bit more. So what you would do then, you may up it. You may start with around 25%, and you may have to up it to 50% or even higher. So you'd alter these by at least 10% each time. So for this example, I've altered that one. It's good at the rear, but it's just slightly out again. So I would alter this again, and until I have 12 o'clock after DTS. So what you do, it's that if you're using DTS, it's after DTS that counts. If you're not using DTS, it's the rear galvo that counts. So they're just examples of cross-level settlement compensation. And I've put a note on the bottom, DTS, if you've got variable DTS, high rail mode, high rail variable mode and DTS standard mode also account for cross levels. So they will reduce or increase the static load that DTS applies depending on the cross level. So that will also make things easier for you. Finally, the last part of the presentation is have a look at some of the benefits of settlement compensation. Well, the first one is improved track quality, because we are hopefully going to be a lot closer to our design position, like I showed you at the beginning. We're overlifting it, so after settlement, we want to be closer to our design position. The biggest benefit is increased longevity, so you would need to intervene less. It's more economic, and you reduce the damage to ballast, because most ballast damage occurs during settlement, not actually the tampers penetrating the ballast. People tend to believe ballast damage is just the tines going in. It's not. It's dynamic settlement under trains, because it's an uneven settlement, and you've got different speeds, axle weights, tonnages, different behaviours, camp deficiencies. So dynamic settlement is very uneven. And also increased track position accuracy, which I'm just going to go through in shortly. Now, firstly, I've just wanted to show you some results of using settlement compensation. So this was DTS settlement compensate. Now, admittedly, this was with using DTS, but the best way of using, I found the best results you will get out of any sort of overlift is to use it with DTS. So the two together, if you use DTS on its own, you get good results. If you use Overlift, you will get better results than conventional tamping, not quite as good as DTS. If you use them two both together, then I found the results are pretty incredible. And this example, I've got 3 examples, and this one's a really good one. This was a multiple wet bed site with a condition of track temporary speed restriction on. Now, as you can see from the bottom, if you look at the bottom of the graph, we've got a satisfactory that goes immediately from the next run into very poor. So you can see you've got a very high deterioration. So then there was manual intervention, which brought it from very poor back into poor. But again, it's dropped 2 bands in one run. So you've gone from poor to super red. It's recorded super red, and I can see it getting steadily worse, 5.1, 5.64. The SD value then ends up at a very high 6.11, hence the temporary speed restriction. So what we did an intervention with DTS and settlement compensation at 50%. And we had an improvement from it's a massive improvement actually, from 6.11 from a super red to a good. Now this is on quite old track. I think this was 2005 by memory, and it was stone blowing track. But because the track had gone that bad because of the wet beds, we decided it wasn't really even responding to stone blowing. We excavated the wet beds and put DTS in. I used very strong DTS, probably the strongest I've used, to give it really good consolidation. But as you can see, it was deteriorating 2 bands previously, but we had another run and it was still in the good. So we decided on another DTS intervention because we planned to, because we thought it would take 2. We didn't realize how good it would end up. And as you can see, the longevity is quite incredible. It was good till this was August. It was good till the following March, and even the year after, in the November, it's still unsatisfactory. So we're looking at 16 months later. Yeah, 15 months later, and it's only dropped 1 band, where we were dropping 2 bands in 4 weeks. So as you can see, if you use settlement compensation and DTS together, you can see the results there, quite phenomenal. This was on a high camp deficiency curve. We had a real problematic poor rate from there. And what tends to happen is when you've got poor rates, you've got faults in the track that are long standing, you have something called ballast memory, where the compaction under the sleepers almost like remembers what it was. So if you come in with a tamper, and again, I'll go back to the start of it, and you intervene with some lifts, and they're generally quite low lifts, 17, 18, 19, 20. So there's 2 things that happen. Because we're not giving the stone enough room to rearrange, it will fall back into its ballast memory, and the fault will, under traffic, the fault will reappear quite quickly. Again, we use DTS with settlement compensation, and as you can see, that poor rate not only went to good, but again, you can just see the deterioration rates. This was June. The following, you're talking 18 months later, and it's still in good, which is just phenomenal. And this was an S&C job actually, so I thought I'd apply it to S&C as well. And I really like this historical graph because we're looking at the top and the third graph down. The top graph is worst top 35 meters, shortwave top basically. The third graph down is mean top over 70 meters, which is our long range filter. Now, as you can see, the high deterioration rates, but when we use DTS in conjunction with Overlift, DTS settlement compensation, I should say, we then got again into good track. I mean, if you look at the third graph down, the mean top was actually very poor. So we went from very poor to good. It's not only the improvement, you can see the difference in the decreased deterioration rates of the track. So to me, these are 3 really good examples. Now, what I'll move on is to increase track position. And what normally happens is during a renewal, and anyone that's worked in maintenance and done a lot of handovers or takebacks, as they're called now, they will, if you check your as-builts, particularly through structures and platforms or over bridges, wherever, they're never quite what they are, particularly the vertical ones, the level. And what happens is the tracks attempt to design tolerances on the night, and technicians walk away and think, yeah, that's great. And when it comes to the take back, things aren't quite right. The track is always lower to design. And again, it goes back to the start of the presentation. It's all about track settlement. People use tampers for years and just do not understand track settlement. And this is why as built, generally, the track is generally lower. This is why we have a lot of issues with platforms as well. Track can be tamped or stone blown to our X and Y tolerances. Toxies, train operating companies use stepping distances. Several weeks later, you could be non-compliant. Again, because of settlement. Stone blowing platforms is a really interesting thing, particularly on rural routes where, yet say, if you've got a rural low speed route, every train stops in a platform, and you've got no freight, for instance. So you've got very low dynamic forces, very low tonnage. You may have maximum of 17-ton axle weights. So the settlement will take considerably longer, for instance, than if you were on a section of category 1A track with 25-ton axle loads and quarry traffic. So you could be on a rural platform where you stone blow it, and due to the residual lift and your design lift, and that could take that long it could take weeks. And then as the track settles, you then become compliant, then will settle below your distances and non-compliant. I've been trying to explain to gauging engineers that it's all about we'll do work and it will generally be non-compliant with a view to it settling to become compliant, and people are now just starting to get the message. So what I'm coming to here is we had a platform installed at Marsh Barton, and they were having problems achieving design. I think they wanted a really tight tolerance of 5 mil vertically, which anyone who's tried to install track to 5 mil vertically will know it's a bit of an unrealistic ask, actually. So what I did, I opted for the settlement graph purely because of what I said earlier. It was erring on the side of caution. This graph settlement is a little bit lower if you use this graph, so I use that formula. I could have used the 1.5, I could have used the remaining lift formula, but because it was the first time I'd done it in a trial, I didn't want to go in all guns blazing. So I used this graph, and what we did, so the graph, as I said, it's got an empiric settlement for it's 4.2, the logarithm of the lift minus 4. Now what I did is stealthily found this equation in one of the books and applied all the DTS settings to it, because this was a DTS job as well. So I added settings for the frequency, for the vertical load, for the working speed, and the eccentricity. And it's sort of like it only tweaked the occasion by small values, actually. It was barely worth, I didn't realize it didn't make a huge amount of difference, but it did make a difference to the settlement. And here's what happened. So this is through the Marsh Barton platform. So what we did, we had our design lift, we had obviously our chainage, we had our design lift. I then applied 100% DTS overlift. So we got our total lift. So let's have a look at the max lift. So if you look down to about 980 on the chainage, our design lift there was around 25.7 mil. 100% overlift. If we go back to that overlift graph, applied a 10.5 mil overlift, resulting in a total lift of 36.25. Now, I calculated that the settlement would be using the graph 12.144. So our net lift would have been 23.9 mil. In reality, it was a little bit lower than that. It was 2 mil lower than that. So I was quite glad I had on the side of caution. But if you look a little bit further up to around most of them, they're all about 5 mil below. And it's sort of like goes with that graph again. It does undercompensate it. But what the point of this is, had we not applied that overlift, instead of being 4 or 5 mil low, you would take that overlift off. So we would have been more like 10 or 12 mil low. So we were virtually on the tolerance. If you can see there was a few 5.8s. So we got very close to our design tolerance. But what my point is, had we not calculated these estimated settlements and took into account the overlift. So we applied overlift, thought it'd settle like that. According to the results, it actually settled lower than which didn't surprise me again, because like I said, I erred on the side of caution, because I'd sooner be a little bit lower than design than above it. But what the point I'm getting across there is, overlift is really good to allow for settlement, to compensate for settlement, like it says, and then you can give your as-built back a lot closer to your design. And in this situation, the beauty was, because it had been DTS'd, we knew DTS gets rid of most of the settlement very quickly, so that track was unlikely to settle much more than what it was. So it's, again, overlift is a really useful tool for increased track position accuracy, because it accounts for settlement. So this is just a summary. Accurate. So it accounts for settlement. If you're using overlift with DTS settlement compensation, it's consistent, it's of a higher quality, and it's increased durability purely because you've DTS and you've settled the track. However, you can still use it without DTS, so you'll have dynamic settlement. It's a bit more uneven. You'll increase the ballast damage, but this is what we do on our conventional tamping. Our settlement's uneven. We damage ballast. It will be a lower quality than DTS, but using overlift, even without DTS, will be certainly a higher quality and more longevity than conventional tamping. So I'd advocate it. I'd advocate it anyway, particularly when doing track positioning. So I was trying to get that point across. I think that literally brings me to the end of presentation. I've got one more slide, I think. What is required when using DTS? Well, I hope we've covered all this. We want our tight clearance data, don't we? We want our overhead, are we under overhead lines? And just to go back as well, we've been using DTS settlement compensation on our overhead lines. So in essence, we've got a max lift of 25 mil under overhead line equipment, unless we get permission otherwise. But what we've been doing, we've been applying DTS Overlift 50%, sometimes more. So we've been applying more than the 25 mil in the knowledge that DTS is settling the track behind it. In our biggest situation, I had permission to do this trial because we had a lot of clearance. We applied 25 mils with 100% DTS Overlift, so it applied around 30 mil lifts. When we DTS'd it, we took the levels, it equated to around a 23 mil lift. So our design lifts were 25. We actually applied 35 after DTS, it equated to 23. So we've got the beauty then of not only applying DTS, but we've got our track very close to our design level, which we wouldn't have unless we overlifted it. So yeah, get your tight clearance data, but bear in mind, if you use it with other pieces, with other technology, you can use it in areas where you compromise clearances, knowing that the track's going to settle. Secondly, sufficient levels of ballast, again, particularly using DTS. Obviously, the more we're going to lift, the more ballast we use. Because of DTS's high compaction, it really consolidates the ballast, so it really chews it up. So if you want to use settlement comp with DTS, make sure you've got good levels of ballast, particularly at this time of the year. You need a placid tamping machine. There's no DTS with those with the methods on that I've explained. Matisa machines don't have a design overlift function, unfortunately. And finally, quite underestimated, you need confidence, which is what quite a lot of people lack, unfortunately. But I think that is about it, apart from questions. So thanks very much for listening, and I hope you all got something out of that.
Thank you very much, Graham. That was absolutely fascinating, and very much very much timely, given the amount of money we spend on on-track machines in a year. It's absolutely necessary that we get the best value from those machines. I was slightly taken aback by design overlift for England. I presume that for some reason you're not allowed to use it in Scotland or Wales, but I may be wrong on that. And also an interesting pulled me up on the fact that the 09 3Xs that we introduced under high output now 20 years old. It just makes me feel old. Anyway, over to questions. We have a few. Lynn Duke has made a very good point in the chat about the difference between stone blowing and tamping. I think I'll leave other people to read that. Callum Burns asks whether has a similar assessment been undertaken where we do renewal on freshly compacted ballast formation. You'll be interested to compare how track that's been recently reballasted it actually behaves. I don't know whether you anything to say on that.
No, well, unfortunately, I work in maintenance, so I haven't really got much control over renewals. We did have a meeting actually, funny enough, last week, where we were trying to introduce it to the renewals fraternity, so they have used it once or twice, but they don't use it very often. So we are trying to get it introduced with renewals. I think DTS and compaction on renewals, yeah, is what is probably more designed for renewals than it is maintenance. Overlift again, it's the benefits of both what I was saying. You get the benefits of the longevity and your track position, because if we overlift and DTS, like I was saying, not only are we getting the good compaction on maybe a ballast cleaning site or a renewal site, we're actually, if we overlift it after settlement, we are closer to our design positions. Yeah, so it is. I mean, it's a really good point, because what I've said there in those last few slides is probably more pertinent to renewals than it is maintenance.
Right. James McCormack asks, is this something we could ask ATG designers, absolute track geometry designers, to apply in the design stage for maintenance on ATG track if we take heights and staggers with Amberg survey equipment?
I actually had a meeting with Errol 2 weeks ago. I should have asked him, shouldn't I? Because Errol McGinley looks after the ATG. If you go back to the one of the last points I said, is we apply DTS settlement compensation under wires, knowing that DTS will settle the track. So initially, our design lifts with our DTS settlement compensation are technically non-compliant, but then DTS comes in, vibrates the track and settles the track right back down to the compliant. Now, exactly the same would happen to ATG, but I'm pretty sure they wouldn't use it. But it's something that I can speak to Errol about. To me, if they did use it, they would get the similar results to us. They wouldn't need to be going back anywhere near as often, because the track will be near the design position, and it will be DT, and it will be properly consolidated. So it's something that would definitely be, I think, a really good tool on ATG. But whether they've got that leap of faith or confidence to start using it, I don't know. Again, it's not I work on Western, but I will run it by Errol when I see him next. Actually, I might speak to him about it next week. That's another really good point. Yeah.
Yeah. Will Francis has asked, what's the main thing you wish designers would do differently or consider at the early stage to aid overlifting?
I mean, it depends where. But if you're talking about structures, it would be or platform. I mean, platforms are the real ones, aren't they? Really, they're the very difficult ones to get right. One of my criticisms, and I'm not critical of it. One of my criticisms I've in the past of designs is it sometimes don't take into account of how you're going to maintain something. So we design something and we're compliant, but when it comes back, sometimes it's not that practical to maintain. So what I would like with people designing is just have a thought for maintenance, for how we're going to maintain it, and also, yeah, whether we can use technology there. So if we are designing something, can we design it with a bit more room? We don't need to have it that high just because we can. So we can use an overlift system, or we can use a DTS system. So to answer the question, sometimes we design stuff that are perfectly good designs and compliant, but at the same time, we don't take into enough account of how it's going to be maintained. I mean, I can do certain switch and crossing layouts where we've got ladders. Slough West is a really good one. we've got ladders. Now, when you're tamping, you need a ladder to go right over to one side and then right over to the other, because you're parallel tamping in a certain direction. You've got the machines on. And what happens is this ladder goes halfway across one way and halfway, it's a trailer and then a facer, whereas you should have a facer and a trailer, you know, with a gap in between. So it's virtually impossible to tamp without four machines properly if you want to parallel tamp over all the type bearers. Or another good example, nothing to do with tamping or what we're talking about, but just about design, is sometimes we design back-to-back switches that are pre-drilled for IRJ 60, 40. Yeah, if it's in a stress layout, how do we stress the fronts of those switches when they're already pre-drilled, because we can't cut anything off? Do we use rail? So there's or you know, where we've got small gaps between switches. So there is stuff I've seen in the past where everything's compliant, but we don't really have to think about how we're going to maintain it.
Okay, thank you. Dominic Greenop makes a couple of points about when he worked on high output track renewals, about the 093X's work to a set design and apply lifts and levels accordingly, and then they would often use two passes in renewals to put the track to line and level. And when ALC and DTS were used on various sites. I think those are points rather than questions. I think John Paul use overlift with larger lifts, but in the range 40 to 60 millimeters. So getting on to the maximum sensible lift would ever apply with a tamper. Would you use design overlift with lifts in that sort of range?
It depends. It depends on various things. On the clearances, certainly not on the wires. To me, you don't need to. The overlift you apply should be pertinent to what settlement you think, estimate, or calculate. So there's no point in, if we're going to calculate or estimate a settlement at being, I don't know, 12, 15 mil, there is a bit of a point, because you probably get more longevity, but you've got to think about ballast levels as well. So the answer to that question is no. I wouldn't, because current ballast levels, we have a massive problem with ballast as it is, particularly in the summer, and we don't really need to. I think if we stick to the realms of what we estimate settlement to be and go from there, we're getting the best of both worlds without compromising ballast and clearances. So the answer to that question is no. I wouldn't do overlifting higher than those values just for the sake of it.
Okay, thank you. Any more questions? Would anyone like to ask a question? And stick your hand up if you would like to, or put something in the chat. Looks about as at 13:30, so pretty much scheduled end time. We appear to have run out of questions. Oh, sorry. I'm Ivan from Uganda has asked whether we would apply design overlift on track with steel sleepers. Interesting question.
Yeah. There's no reason why the critical thing tamping, and it's more critical on steel than anywhere else, is getting your tamping depths right. So there's absolutely no reason why you couldn't apply it on steel sleepers, but you would have to make sure, because if you're applying you just got to be a little bit careful with the lifts. Actually, there's no reason why you can't apply it, as long as you don't go silly with it. If you apply, if you look at some of the values on there, some of those overlift values are just 10, 12 mil, but that 10 or 12 mil makes a huge amount of difference to get to your design level for longevity. So the answer to the question is yes. Make sure you've got enough ballast, and make sure you tamp at the correct levels, particularly the shallow depths that steel sleepers are.
Okay, thank you, Graham.
Okay.
I think we're John Paul Coffey has asked, what's our next presentation? So far, all three have been great. I have to confess, John Paul, I don't know what our next presentation is. I'm sure it's on our website. thepwi.org. So yeah, I think best to have a look on the website. I'm sorry I can't answer your question directly. Well, again, thanks again, Graham, for a really interesting presentation. I think we've had a big audience. We've been up in the 90s, so there's plenty of interest, and I think opening the eyes of the UK on-track machine community to design overlift and its various forms is a great thing to do. Thank you
No,
very
thanks
much
for inviting
indeed.
me. That's a pleasure. Thanks, Stephen.
Done. So if everybody's happy, if everybody's happy to go back to work, we'll